Hello and welcome to part 2 of our discussion on the concepts of circles. In this lecture, we will learn about the chords of the circle, the tangents to a circle, and the relationship between the chords and the tangents. Let's begin by talking about the chord of a circle. Now, the chord is a pretty straightforward idea. It is any line that connects 2 points on the circumference of a circle. For example, line AB here connects points A and B that lie on the circumference of the circle, and therefore AB is a chord. Similarly, line CD here is also a chord. Notice that line CD is slightly longer than line AB. And line EF here is also a chord, but you might argue that it's the diameter because it's going through the center of the circle. And that's perfectly fine because the diameter by definition is the longest chord in a circle. Now let's learn about some of the important properties that occur when we draw chords in a circle. The first thing that we'll talk about is the perpendicular to the chord. Let's draw chord AB here. I'm going to drop a perpendicular from point O, which is the center of the circle, down to AB. The line OC will be perpendicular to chord AB. And this perpendicular OC will end up dividing the chord AB into equal halves. It'll bisect the chord. Therefore, we can say that AC is going to be equal to CB. So remember, the perpendicular from the center onto the chord always bisects the chord. Another important thing to understand is that if I were to connect line OA, that would be the radius of the circle, and also connect OB, that would also be the radius of the circle, we end up with the triangle AOB. This triangle AOB is going to be an isosceles triangle because two of the sides, AO and OB, have the same length. They both are equal to the radius. And because this is an isosceles triangle, the angles OAB and OBA will be equal in measure. So remember, anytime you draw a triangle such that one of the sides is a chord of the circle and the other two sides are the radius connected from the endpoints of the chord onto the center, this will always create an isosceles triangle inside the circle. The next thing that we will need to discuss is about chords that have the same length. Now remember, two or more chords that have the same length will always be the same distance from the center of the circle. So for example, chord AB and chord CD here, if I tell you that the length of AB equals to the length of CD, then the perpendicular distance from point O to AB will be the same as the perpendicular distance from point O to CD. What that means is that if you were to draw a perpendicular from point O down to AB and measure that distance will be the same as the perpendicular distance from point O to CD. Also remember that the perpendicular acts as the bisector of the chord. What that means is that AE should be equal to EB and that CF should be equal to FD. So therefore AE, EB, CF and FD should all have the same length. Now that we know that two chords that have the same length are the same distance from the center of the circle, now let's draw these triangles AOB and triangle COD. The important thing to know here is that triangle AOB and COD will be congruent, which means that they have the same side lengths. And the reason is very simple. Two of the sides of each of these triangles is equal to the radius of the circle, and the third side, which is the chord AB and CD, are equal as well. So therefore, these two triangles are congruent to each other. And because they are congruent to each other, they have the same angles as well, which means that angle AOB should be equal to angle COD. Hence, we can conclude that equal chords are extended or subtended by equal angles from the center of the circle. The next important property is one of the most commonly tested properties in admissions tests, and that is related to the diameter as the chord of a circle. Remember, the diameter is the longest chord of the circle. So let's draw diameter AB here. This is the longest chord that can be drawn inside this circle. And the diameter divides the circle into two halves, both of which are known as semicircles. If I were to draw a triangle using the diameter as the base and touching the circumference on either side, that triangle will always be a right-angled triangle. So for example, triangle ACB here is going to be a right triangle where angle C is 90 degrees. I can draw it at any side, either above or below, as long as it touches the circumference. For example, triangle ADB here, that will also be a right triangle. If I draw it below, like triangle AEB here, that is also going to be a right angle triangle, and triangle AFB here will also be a right triangle. So remember, the diameter always extends a right angle triangle onto the circumference of the circle. The next important thing that you need to understand is the angles extended by the same chord. Now remember, when angles are extended by the same chord onto the same side of the circumference, on the same side of the circle, those angles have the same measure. So for example, if I use chord AB here to extend angle C onto the circumference, and if that angle is X, then any other angle extended by AB on the same side of the circle will also have a measure of X degrees, which means that if I were to extend angle D here, then that would be X degrees, and angle E here will also be X degrees. As long as you use the same chord and you extend the angle onto the same side of the circumference, you will get the same angle. So therefore, angle ACB equals ADB equals AEB, and they're all equal to X degrees in this case. And if the angle had been extended on the other side, for example, if I extend angle AFB and that is Y degrees, then any other angle extended on this side will also be Y degrees. So we can say that AFB and AGB are equal, and they're both equal to Y degrees. And also remember that when angles are extended on opposite sides of the circumference, on opposite sides of the circle by the same chord, they are always supplementary, which means they always add up to 180 degrees. Therefore, we can say that angle ACB and AFB, because they are extended on opposite sides of the circle, they will add up to 180 degrees. Or we can say that X plus Y should be equal to 180 degrees. Here's a question based on the idea of angles extended by the same chord. The question says, if angle ACB is 60 degrees, then find angle ADB and angle AEB. I want you to try the question yourself, so please pause the video, and once you're done, you can watch the solution. And here's the solution to this question. We are told that angle ACB is 60 degrees, so therefore we can write ACB as 60 degrees, and the question says find the value of angle ADB. Now as you can see, angle ADB is extended by the same chord AB and on the same side of the circle as well. So we know that whenever a chord extends two angles onto the same side of the circle, then the two angles are equal in measure. So therefore, if angle ACB is 60, then ADB should also be 60 degrees. So the answer to part A is 60 degrees. Now let's focus on part B. The question says find the value of angle AEB. Angle AEB is also extended by the same chord AB, but it's not on the same side, it's on the opposite side. And we know that when angles are extended by the same chord but on opposite sides of the circle, then they are supplementary, which means they add up to 180 degrees. So therefore, the value of angle AEB should be equal to 180 minus the value of ACB, which is 60. That gives you 120 degrees. So the answer to part B is 120 degrees. I hope this concept is clear to all of you now. And now that we understand that two angles extended by the same chord but on opposite sides of the circle are always supplementary, this is an excellent time to understand the cyclic quadrilateral. The cyclic quadrilateral is a quadrilateral whose vertices are all on the circumference of the circle. When you create a quadrilateral like this, then there are obviously four angles being created. Let's call them angles A, B, C, and D. And the angles opposite each other are always going to be supplementary. That means they will add up to 180 degrees, which means that A plus C should be equal to 180 degrees and B plus D should also be equal to 180 degrees. Now, why does that happen? Well, the reason is very simple. If you remember the rule that I've just written above, two angles extended by the same chord but on opposite sides are always supplementary, and I draw the first chord AC, then the angle above is angle B and the angle below is D, so B plus D should add up to 180 degrees. Similarly, if I draw the second chord, which is BD, then again there are two angles, one on the left, angle A, and one on the right, which is angle C, and they should also add up to 180 degrees. Therefore, angles opposite each other in a cyclic quadrilateral always add up to 180 degrees. Another very important property, but very easy to remember, is the relationship between the angle extended at the center of the circle and the angle extended at the circumference. The rule is that the angle extended at the center is always twice of the angle extended by the same chord onto the circumference, which means that if I was to extend the angle ACB from the chord AB, and if the measure of that angle is x, then the angle extended from AB onto the center, angle AOB, will be twice of x. So angle AOB is 2 times of angle ACB. The angle at the center is always twice of the angle extended by the same chord onto the circumference. Now, when these two triangles are drawn extended from the chord AB, triangle ACB and triangle AOB, you will observe a figure emerging that we've studied in the quadrilaterals. And this is this particular figure that I've highlighted here. This is known as the arrowhead. And there's something very interesting that happens with the angles in the arrowhead. Let's discuss what happens. So the idea is that when you draw an arrowhead like this, which is drawn in such a way that vertex A and B and C are on the circumference of the circle and vertex O is in the middle at the center of the circle, then the angles at the corners at the tail, the angle A here and the angle B here, these two angles, when you add them together, you get the value of angle C. So what I'm saying is that angle ACB, which is the angle at the top here, is equal to angle OAC, which is the angle here, plus the angle OBC, which is the angle here. Right? So if OAC is A degrees and OBC is B degrees, then angle C or angle ACB will become A plus B degrees. And why that happens is very simple. Let's draw the line OC. Now OC is the radius of the circle and OA is also the radius of the circle. So when we take a look at the triangle on the left hand side, this triangle is an isosceles triangle. And remember, in an isosceles triangle, the corresponding angles are equal. So if the angle at the bottom here is A, then the angle at the top here should also be A. Similarly, the triangle on the right hand side is also an isosceles triangle. Side OB and OC are both the radius. So if the angle on the bottom here is B, then the angle at the top would also be B. And that's why angle ACB will be equal to A plus B. And also remember the fact that because these triangles are extended by the same chord, which is chord AB, and since the angle at the center is always twice the angle at the circumference, if the angle at the top, ACB, is A plus B, then the angle AOB, which is at the center, would be twice of A plus B. Now let's discuss tangents of a circle. A tangent is a line that just connects with the circle at a point on the exterior of the circle, never enters inside the circle. So it's a line that is just touching the circle at the exterior on the circumference, never goes inside the circle. For example, line AB here is tangent to the circle. Similarly, line DE here is also a tangent. And the point at which the line connects with the circle, that is known as the point of tangency. So point C here is a point of tangency, and point F here is the point of tangency for tangent DE. Another important point to remember is that whenever you draw the radius from the center to the point of tangency, for example, line OC here or line OF here, the radius at that point is always perpendicular to the tangent. So remember that the tangent is perpendicular to the radius of the circle at the point of tangency. The other important point to remember is that if you have two tangents drawn to a circle and those tangents are not parallel, for example, the two tangents that I've drawn here, they're not parallel to each other, and if you extend them, they will eventually meet. And the point at which they meet is known as the origin of tangents. So remember, any point outside a circle can extend exactly two tangent lines to the circle. And the distance AB and AC will also be equal. So the distances from the origin of the tangents to the points of tangency are always equal. The third thing is that this figure that we've seen inside, figure ABOC, this is in the shape of a kite, which is a quadrilateral. And the sum of angles inside a quadrilateral is always 360 degrees. Now we know that angles B and C are 90 and 90. 90 plus 90 adds up to 180, which means that the other two angles should also add up to 180. So therefore the angle BOC and the angle BAC should add up to 180 degrees. In this case, x plus y should be equal to 180 degrees. Now let's learn about something called the Tangent-Chord Theorem. To help you understand this theorem, I'm going to give you a very simple example. Let's begin by drawing a diameter AB here. And we know that diameters always extend a right angled triangle onto the circumference. So let's make that triangle. So we know that angle ACB is equal to 90. Let's also mark angle A as x degrees and angle B as y degrees. Now, since the sum of the angles inside a triangle is 180 and angle C is 90, that means angles A and B should also add up to 90. So therefore, x plus y must be equal to 90 degrees. Now we're going to draw the tangent at the bottom of the circle. Let's call that tangent DE, and this tangent meets the circle at point B. Now the angle ABE or OBE should be equal to 90 degrees because we know that a tangent is always perpendicular to the radius. So therefore, angle OBE is 90. Now, apart from that, if I look at the angle to the right of y, which is angle CBE, and I mark that as angle Z, then we can say that y plus z should also be equal to 90 degrees. Because remember, OBE was 90, so y plus z should also be 90. So we know that x plus y is 90. We also know that y plus z is 90, which means that x and z should both be equal to each other. So therefore, we can say that x is equal to z. Therefore, we can say that angle BAC is equal to angle CBE. This brings us to the Tangent-Chord Theorem. The Tangent-Chord Theorem tells us that if you draw a tangent, tangent DE in this case, and you draw a chord, chord BC in this case, then the angle between the tangent DE and chord BC is always going to equal the angle extended by chord BC onto the opposite side. Therefore, angle Z will equal angle X. Now let's understand the Tangent-Chord Theorem in greater detail. The Tangent-Chord Theorem, which is also known as the alternate segment theorem, states that for any circle, the angle between a tangent and a chord is equal to the inscribed angle on the opposite side of the chord. What does that mean? Well, let's take a look with the help of an example. Let's draw chord AB. And let's draw a tangent to the circle at point A. Let's call that tangent DE. Now the angle between the tangent and the chord in this case would be the angle BAD. Let's mark that. And let's assume that this has a degree measure of x degrees. Now this angle, which is the angle between the chord and the tangent, has to be equal to the angle extended by the same chord onto the opposite side, which means the angle extended by chord AB onto the right side of the circle, which in this case is the angle BCA. This would also therefore be x degrees, which means that angle BAD is equal to angle BCA. You can observe that actually there are two chords that are connected to the tangent. There was chord AB and there's also chord AC. And the angle between chord AC and the tangent DE is going to be the angle CAE. Now let's mark that as y degrees. So this particular angle, angle CAE, is going to be equal to the angle extended by the chord AC onto the other side, which means to the left side of the circle. And that's going to be the angle CBA. So if angle CAE is y degrees, then CBA is also going to be y degrees. So we can say angle CAE equals to angle CBA. Let's understand this concept with the help of another example. The Tangent-Chord Theorem tells us that the angle between a tangent and a chord is equal to the inscribed angle on the opposite side of the chord. In this particular case, we have been given three chords. There's chord AB, BC, and AC, which combine together to form a triangle with the angles 40, 60, and 80 degrees. I'm going to draw a tangent at point A, and I'm going to call that tangent tangent DE. Now remember, we're supposed to figure out the angle between the tangent and the chord. So let's focus on chord AB. So the angle between chord AB and tangent DE is going to be the angle DAB. This angle is supposed to be equal to the angle extended by the chord AB onto the other side, which means it's supposed to be equal to this particular angle, angle 80. So we can say that angle BAD is going to be 80 degrees. DAB or BAD is 80 degrees. Now let's focus on the other chord. The other chord is chord AC. So the angle between chord AC and tangent DE is supposed to be the angle on the right side, this angle that I've highlighted in yellow, and this angle is supposed to be equal to the angle extended by the chord onto the other side. Now chord AC extends the angle on the other side. That angle is 60 degrees. So therefore this angle CAE or EAC should also be equal to 60 degrees. I hope this concept is now clear to you. So here's a question for you based on the same idea of the tangent-chord theorem. The question here has given us a circle with a triangle ABC inside it, and there's a tangent DE which connects to the circle at point C. The question says find angle BCE. I want you to pause the video and try the question yourself before you see the solution. And here's a solution to this question. The question says find angle BCE, which is the angle on the outside between the chord BC and the tangent DE. We know that the angle between a tangent and a chord is equal to the inscribed angle on the opposite side of the chord. The chord that we're talking about in this case is the chord BC. So what angle does chord BC extend on the other side? Well, that's angle A, which is 84 degrees. Therefore, angle BCE should also be equal to 84 degrees. So the answer is 84 degrees. I hope that the tangent-chord theorem is now finally clear to you. And this concludes our discussion on the concepts of circles, specifically tangents, chords, cyclic quadrilaterals, diameters, the angles extended by the chords, and the tangent-chord theorem. I hope all the concepts were clear to you. If you still have any issues, feel free to raise them in class. Thank you and take care.